Hi. So there we are, yeah. So that's who I am, but we've already been through that. So I'm going to talk about GPUs today. And so the first question that my presentation will ask is, why do we want one? Physical or virtual, why do we want a GPU? Well, there's obviously heavyweight apps like something like CATIA or AutoCAD, to name a couple of apps. But they clearly need a GPU, but we also need a GPU for things like this. So yeah, just running a website like this inside Chrome will make use of a GPU on the system if there is one. And if when we run something like that, we can see on the CPU that it's not particularly busy. It's not doing very much. That was just rendering a website. But if we turn off Chrome's use of a GPU, which we can do, then just displaying the same website, we can see that the CPU usage is now almost doubled. So if we think of an enterprise or a cloud hosting hundreds of virtual machines running desktops, if all the users kick off Chrome just to display a website, or Google Earth or something like that, then it's going to hit the server CPUs quite hard. So it's very useful if we can give the VMs GPU cycles as well, because that will essentially halve their CPU usage, and it increases our scale before the system CPUs become overloaded. So what do we mean by a virtual GPU? Well, this is the definition I've always used. A virtual GPU is an emulation of a GPU that internally makes use of a physical GPU. But before we move on with an explanation about that, I'd just like to cover how I/O emulation works inside Xen as some background. Now let's first look at the major components in Xen. Now Xen is a type 1 hypervisor, so it sits in the middle and it runs directly on the hardware. But it's more like a microkernel than a fully functional OS. So up in the top left there we have DOM, which is short for domain, 0. And that is always the first virtual machine to be booted, hence the name. And it owns most of the hardware. All the peripheral devices are delegated to it. Now, so it's a full OS, and it contains device drivers for peripheral hardware. Now, we don't want to implement device drivers directly in Xen, so this is a useful concept for us. Now, DOM0 is a full OS, but the core and, the CPUs and the memory of the system are owned by Xen and delegated to it, so how do we do that? Well, DOM0 is running what's called a paravirtual OS, that's it's enlightened, so it knows that it's running inside a VM running on Xen, and it uses paravirtual interfaces to talk to CPU and memory. And in XenServer we use a Linux DOM0, and since early Linux 3.x, the upstream kernel has had all the necessary enlightenments to allow us to run it as domain 0. Now over on the right we have DOM-U. Now the U stands for unprivileged, and sometimes DOM-U's are referred to as guests, and I'll refer to them as guests in this presentation as well. Now they're generally one of two flavors. They can be a paravirtual guest, meaning they have the same enlightenments, they know that they're running inside a virtual machine, or they can be HVM, that stands for hardware virtual machine, which means that they are either completely unenlightened, they don't know that they're running inside a VM, or they have some paravirtual enlightenments, but they're not complete. One of the things that a hardware virtual machine might do, for instance, is it might try to talk to standard IDE hardware to just boot itself to mount its system disk. But how do they do that? Because they're not privileged, they can't talk to the real disk. So how do we actually make them work? Well, we run QEMU. QEMU can be a full machine emulator, but for supporting HVM guests in Xen, we don't use it as a full machine emulator. Xen's the machine emulator. We just use QEMU as a device emulator. And it's quite a comprehensive device emulator containing models for most traditional I/O hardware. For example, it contains a model for an IDE disk. So the guest, for instance, may use an IDE disk, so it's going to do something like when it first starts to boot, it's going to issue port IO ins to go and retrieve disk blocks. Now these are tracked by Xen, as we can see down here. My pointer's not particularly good. And then they're forwarded to QEMU, and QEMU can then use a virtual disk image, read the data out of it, and then pass that back to Xen so it can complete the guest's in instruction. Now it's also worth noting that because QEMU is running in a domain that has privilege over the DOM-U, that the QEMU instance can also map the guest memory, and so we can also emulate DMA inside QEMU. But going back to the I/O accesses, how do these actually get forwarded from Xen to QEMU? Well, it all centers around the data structure called an I/O rec. Now, Xen sets up a shared page between itself and QEMU, and these contain I/O rec structures, one per guest virtual CPU. Now, when a guest vCPU attempts some form of I/O, Xen traps that I/O, fills in the I/O rec structure to describe the I/O, pauses the vCPU, and then passes that information to QEMU through the shared page. Now let's have a look what's in the structure. Now, the structure itself contains many fields, so let's go down to some of the key ones here. Now, the first field says whether the I/O is a read or a write. The next one tells us whether it's a port I/O, memory mapped I/O, or a PCI config space access. Now, Xen handles the abstraction of PCI config space internally, so standard Intel emulation is port I/O to CF8 or CFC, and Xen abstracts those away and passes the access to QEMU as if it's just an abstract PCI config access. Then we have either a port number, an address, or a config space register offset, a size, a count. Now, the I/O may be done by rep instruction, so the actual access there may be multiple accesses issued by essentially a single instruction. The data, sometimes the I/O has immediate data in the instruction, but if it's not data, then it's a pointer to somewhere inside the guest memory to find that data. And then we have a state field, and this is used for handshaking between Xen and QEMU. It's set to a value called I/O rec ready when Xen is ready for QEMU to do some emulation, and when QEMU is finished, it sets it to a value called I/O resp ready, i.e. response ready, and then passes the data back to Xen. Now, internally, QEMU has a registration mechanism for various device models for disk, network, various other peripheral hardware, and the emulations are rooted inside QEMU using essentially these top four fields, which is the direction, the type of access, the address of the access, and the size. But we could actually have a look at routing I/O separately in Xen using these same fields. So we need to route them to more than one emulator, and this might actually be useful. So we had some new hypercores into Xen called the Irf Server Api. Now this essentially means that QEMU just becomes one Irf server. In other words, it's essentially an emulator that may be one of many emulators in the system. It then registers its device models directly with Xen, and then Xen can route the I/Os either to QEMU's device models, or if another emulator is essentially run on the system, then it could route those IRX to that secondary emulator by I/O port, MMI address, PCI config register offset. Now let's recall our definition of a virtual GPU. Now, using the Irf Server API, we're no longer required to implement the GPU device model in QEMU. We can now build an integrated virtual GPU stack using a secondary emulator, and this turns out to be a very useful thing. Now, another piece of background I should go through before I carry on is graphics stacks and Windows. Now, in XenServer, virtual GPUs squarely aimed at Windows. It's our main use case. So we should broadly understand how graphics stacks work in Windows, but it turns out that Linux is not actually all that different when it comes to the way that graphics work. Now this is the classic picture of the Windows display driver model, which is just taken from the MSDN website. And we're interested in the grey boxes. We'll ignore the OpenGL one. We're interested in that one at the top saying user mode and that one at the bottom saying display mini port. Now the driver model is essentially split across the user kernel boundary. User mode part is basically a library that runs in context of the application processes. And then the kernel mode part sits there in the Windows kernel, and it is the part that talks to the GPU hardware. The important thing to note is that both of these are supplied by the GPU vendor, and the model allows for vendor-specific access between the two, so logically they form the graphics driver between the pair of them. Now, if we abstract away from the specifics of the WDM into sort of a general model, we can see what the user and kernel mode components essentially do. Now, the user mode part is responsible for taking the API calls, the graphics API calls from the application, and turning them into GPU commands, which it then inserts into a queue for the application. The kernel mode part sits there and looks at all the various GPU command queues for each of the applications, schedules them, and dispatches those commands to the GPU itself to actually perform the operations. But what if we run Windows in a what if we were to run Windows in a virtual VM, sorry, in a VM? Now that could be running in a VM, so the application could be in a VM. And what if the kernel mode part scheduled commands queued by an emulator rather than directly by an application? Well, we can essentially virtualize our system using these two ideas. So we can redraw our diagram. Now what we had before, our Windows OS is up in the top left inside of DOM-U there, and we've now introduced Zen and the DOM0, which is talking to the real GPU hardware. Now the guest user mode driver is the same. It really doesn't have to change. It still takes API calls from the application, turns them into GPU commands, and queues them. But the guest kernel mode part is now no longer talking to a physical GPU. Instead, when it dispatches commands to what it believes is the GPU, those commands now go to an emulator. And the emulator can then queue those commands on behalf of the guest. So the emulator in DOM0 is logically the user mode component of the graphics stack in DOM0. And then the kernel mode part of the DOM0 graphics stack can dispatch those commands to the GPU itself. And that way, we can now not only run multiple applications on the GPU, we can run multiple applications inside multiple VMs on the GPU. And so, let's go to our first example of a virtual GPU, which is Intel's GVT-g. Now, this is the only open source virtual GPU implementation that we have in XenServer. So it's the one we know most about. And before I carry on, I just want to acknowledge some of the guys at Intel, mostly in the Shanghai Development Center, particularly Kevin, Jiwan, who've helped me over the years integrate this into XenServer, and it's some of their material that I've used to formulate these slides. Now, Intel GVT-g works on the Iris Pro chipset. Now, that's a GPU that's integrated into the single-socket variant of an Intel CPU. And these chipsets can not only be found in desktops or NUCs, but they can also be found in blade servers, which is where XenServer's main interest is. And this is a simplistic view of the Iris Pro architecture. And the important thing to note when you look at this diagram is that there's no memory. There's no dedicated VRAM. Instead, it uses host memory because it's tightly integrated into the CPU. So the CPU and the GPU are on the same die, and the host memory is accessed through a shared level 4 cache, which is how the speed is maintained. The GPU does have its own virtual memory space, though, and this is set up using the graphics translation tables, or the GTTs, and they feed into the GPU's internal NME. Now, the GPU appears to the CPU as a PCI device. It's tightly integrated, but logically it appears as a PCI device. And programming the GPU's virtual memory starts with something called the global GTT, or the GGTT for short. And this is accessed via one of the GPU's PCI bars. Now, the GGTT can directly reference GPU objects in memory, such as frame buffers, but it can also contain pointers to what are called per-process GTTs, or PPGTTs, which are per-application virtual address spaces, which also, and these PPGTTs actually reside in host memory, so they're not directly programmed through the device. Now, the PPGTTs can be up to 4 levels deep, and they contain familiar items. They look very similar to CPU page tables, and you walk down the levels, and eventually you access a 4K GPU page at the bottom, so the standard page size for the CPU matches the page size for the GPU, which is kind of useful. So how do we go about virtualizing these things? Well, recall how our emulation is rooted in Zen. PCI config space accesses for the virtual GPU's GGTTs will be PCI config space accesses. So these can be trapped by Zen and forwarded to a device model which can handle them. And this can set up specific handlers for whatever address is programmed into the GGTT bar. So we have a picture like this, is that each of the GGTT, so each of the GGTTs is emulated, and because they're emulated, they can be partitioned, and we can give a slice of them to each of the virtual GPUs. Now the full size of the underlying GGTT bar is exposed to the VM, but the partitioning, because we're emulating, the partitioning can be enforced, and each of the virtual GPUs can actually only access a particular area of that. And the area that's unavailable, the bit in grey there, is called the balloon. This is Intel's terminology, but you shouldn't confuse that with memory ballooning inside guest VMs and Xen. Now the guest, of course, writes guest frame numbers into the virtual GGTT bars, but these need to be translated into machine frame numbers before they can then be programmed into the actual physical GGTT. Now actually the MFNs that I refer to here are actually what are called BFNs, or bus frame numbers, because the GPU actually sits logically beyond the system IOMMU. But I'm assuming here that we're using Xen's default setup, which says that there's a one-to-one mapping between bus and machine addresses. So that's the global GGTT virtualization dealt with. Now recall the PPGTTs. Now they're in memory, and the guest will just write to those directly. So when the guest writes a root pointer to a PPGTT into the emulated GGTT, we now need to walk down all those levels, those 4 levels, and we need to copy the tables aside into what are called shadows, and then translate the GFNs that they contain into MFNs as we go. So you can see from this diagram, we copy them aside, and then we write the root pointer of those shadow copies into the actual GGTT of the physical GPU. So now it has essentially the same view of memory as the model virtual GPU has. Now, note also that we need to remove write permissions to those PPGTT pages as we find them, because if the guest directly updates them in memory, we need to know about it, because we need to do the translation again and update the shadow copy. So we remove write permissions so that Xen can trap accesses. We then emulate those accesses and allow them through. Now, that's the memory components of the GPU virtualized, but we also need to virtualize the actual render engine itself. So, specifically, we need to take the GPU commands that the applications are running inside the VMs are queuing, and we need to audit them and dispatch them to... So we need to audit them and then dispatch them to our GPU in DOM0. Now we need to copy them aside as we do so, because we can't allow the application running inside the guest to modify those commands after we've audited them. Now the backend kernel then takes each of the audited GPU commands from the various VM queues, and it will then actually dispatch them to the GPU as it round robins between the different VM contexts. Now the GPU commands are generally dispatched by DMA, in other words it will tell the physical GPU where the command queue is, and it will ask it to go and fetch and service those commands. So that's broadly how GVT-g works in XenServer. There's one more thing we need to mention, which is the display itself. Now, XenServer normally presents VM consoles via a tool called XenCenter, and this is done via a VNC protocol, very simple. But we need some way to get the guest frame buffer out inside domain 0 if we're going to do this. And obviously if the guest frame buffer is being rendered by the GPU, we need to go and find it. Now it so happens that GVT-g handily maintains a pointer to the guest composite frame buffer inside the GGTT. And what we do is we go and find that there's Intel provide a direct render manager at IOPTL, so we can go and find the base addresses of the frame buffers. And we then copy those into the domain 0 private area inside the GGTT. Now domain 0, as far as GVT-g is concerned, is another guest, so therefore it has its own dedicated area in the GGTT. Now once we've copied those frame buffers, we can then map QEMU's own allocated console buffer, its VNC frame buffer essentially, into the DOM0 GGTT as well. And once we've done that, we can then ask the GPU to blip the frame buffer from where it is inside the guest memory into our console buffer inside DOM0. And as it does so, it also linearizes it as well. Now, the linearizing is quite important. QEMU expects its frame buffer format to be linear 32-bit pixel format, but the guest may be using something else. Now, it so happens the GPU has a useful function called the fence register, which allows you, at the point of blit, to do pixel format translation automatically, and we make use of that. Now, once we have the linearized frame buffer inside DOM0, we can then advertise it to XenServer via VNC, and that console can be displayed. Now, this is the implementation diagram. Just generally shows most of the functional components. Now, the GPU emulator we use inside Xen is called XenGT. And now actually it runs as a kernel mode component inside the DOM0 kernel. Even though it's logically the user mode component of the graphics stack, it's actually a kernel module. Then the DOM0 kernel mode driver inside our logical view of the graphics stack is the standard Intel i9-15 driver, which talks to most of the Intel GPUs. It has some extensions though, which allow it to interact directly with the XenGT kernel module. Now, unfortunately, neither the i9-15 extensions or the XenGT module itself are in the upstream Linux kernel, so we're having to maintain those as patches at the moment inside XenServer. And the VGA is still handled by QEMU, so all the legacy aperture accesses through the BIOS, and all the legacy register accesses done by the guest program VGA, they're still tracked by QEMU. Which makes handling the switchover between the boot time display mode driver and the Intel graphics driver inside the guest slightly tricky. But Intel provides us with direct render manager IOP tools to manage that transition as well. Now, I should like to mention some of the work that Intel are doing on a new architecture for GVT-g. And this is more recent than our integration into XenServer. So what they're doing is they're using KVM as a base for this work because it provides them with a simpler architecture to deal with as they're doing the upstreaming. So let's have a look at what they did. Now, well, the first thing they did was they actually changed the i9-15 driver, quite radically actually, and the KVM GT, so the KVM's logical equivalent of XenGT, is now actually a sub-module of the i9-15 driver itself. It's very much more tightly integrated than XenGT was in the original architecture. Now, this was done at the request of the i9-15 maintainers because it makes life a lot simpler. It means that the i9-15 driver now becomes a single point of resource ownership, whether the thing that's using it is KVM GT or a user mode application running inside an X server in DOM0, for instance. And the resources are now exposed through a new framework, which I think Intel added, called the MDEV framework, or Mediated Device Framework, which is a useful abstraction for QEMU, as we see. The Mediated Device Framework fits into something called VFIO. Now, VFIO is something that was created to allow PCI SRI virtual functions to be easily consumed inside Linux. But the MDEV framework sits inside the VFIO layer and essentially creates fake virtual functions. So, virtual GPU instances are programmed using the provisioned and created using the MDEV framework, so they appear now essentially as these fake virtual functions. They can then be enumerated by whatever is using the MDEV framework, i.e. the thing consuming VFIO, which in the KVM case is QEMU. And finally, the emulated I/O requests that come via KVM to QEMU can now be forwarded through the VFIO framework to the MDEV layer and then on to the GPU emulation model running inside the i9-15 driver. So what about the future Xen implementation? Well, we really want to use these same abstractions. We don't want to reinvent things. So we want to essentially have our own equivalent of the KVM GT module sat inside the i9-15 driver. But we won't get I/O coming through QEMU because our I/Os are coming directly, if you remember, to the XenGT module. itself, but we really want to be able to steer them through the MDev framework in the same way. So I suspect what we'll have is a kernel mode access to that MDev framework as if it was coming from user space, but actually it's coming from kernel space. And then rather than libvirt, which is the tool stack that's used by KVM, we'll use the same MDev abstractions that libvirt is using, but we'll drive them from libxl, which is the default Xen tool stack. I should also mention that there's a new API called DMA buff that Intel have been working on. They talked about it at last year's KVM forum. And this essentially provides a cleaner abstraction to what we are doing to get the frame buffer out that I explained in domain 0. It provides another addition to the VFIO API to manage those frame buffers and copy them around. So, on the interest of balance, I should talk about other virtual GPU integrations we've done into XenServer. And I'd like to start with Nvidia Grid. Now, Nvidia Grid uses a plug-in card. Chronologically, this was the first vGPU integration we did into XenServer. Now, the architecture is not vastly different to the one I described for XenGT, but it uses a user space emulator instead of a kernel mode emulator, and we call that DMU, which the D standing for discrete. It's a single emulator that emulates both the NVIDIA device model and the legacy VGA, which makes handling the frame buffer transitions a little easier. Now, in the NVIDIA device, some of the bars of the hardware itself can be broken down to sections and passed through directly to the guest, allowing the guest to talk directly to the GPU, which means there's less emulation in the way than there is in the Intel case in some workloads. Also, because the NVIDIA card has onboard VRAM, there's no address translation to worry about to allow it to talk to host RAM, and so it can maintain the command queues of the applications running inside the VMs directly. And this means that once you've essentially done application setup, it's, the GPU is servicing that application in more or less the same way as it would be if it was running on bare metal, and so the performance is fairly good. Now, other virtual GPUs, the most recent one we've done is AMD MX GPU. Now, this has only gone into XenServer 7.4, which I think was released a couple of months back, which was, this is the brand new implementation. Now, it makes use of a chipset called Tonga, which is available in the FirePro S7150 and S7150 X2 cards. The X2 essentially just being two S7150s glued together with a single edge connector. Now, this hardware is interesting because it's actually SRIOV, it's physically virtualized. And it can make use of traditional PCI pass-through. Now, remember I mentioned pass-through right at the beginning, which allows us to essentially map the bars of the PCI device directly through to the guest. And then the guest really is talking straight to the hardware. There's one extra extension we had to put into the PCI pass-through code in QEMU to support this, which is just that we needed something to go and provision the virtual function. Now, the virtual functions themselves, when the hardware starts up, are there, but they don't do anything because you need to specifically add them to the GPU's scheduler. So there's a small bit of work done at start of day in QEMU to take the VF that we're passing through and add it into the GPU's scheduler. Now, the S7150 supports up to 16 virtual functions, so the X2 variant, i.e. the two glued together, supports up to 32. Unlike any other PCI pass-through solution, the config space is emulated, but the bars are accessed directly, except for one, unfortunately. Now, one bar is actually just, one virtual function bar, I should say, is actually just one of the physical function bars that's echoed through the virtual function, and therefore it's not actually safe to access simultaneously from multiple VMs. So there has to be a little bit of complexity in QEMU to negotiate access to this one particular bar. Now, fortunately, this particular bar is only ever used during driver load and driver teardown. It's not actually used when applications are running. So this is complicated, but it's not actually a performance issue. And because the device is SRIOV with a schedule, as I said, once the setup is done, the guest and the VF are communicating directly. There's no emulation in the way, so performance is pretty good. However, the legacy VGA in this case is still emulated in the same way by QEMU, and because this is a pass-through solution, the legacy VGA actually appears as a separate device in the system, which is unfortunate because Windows now sees two display devices, and it doesn't behave particularly well in those cases, so there's a little bit of complexity when setting up a Windows VM where you have to go and turn off the display that's linked to the legacy VGA. Otherwise, you end up with your desktop spread across two devices. This is not particularly a problem in the Citrix use case, because mostly we're using this for VDI, so we're installing our own graphics stack into the guest anyway, and that glosses over these issues. Now I'd like to go on to a new thing in virtual GPU, which is virtual GPU migration. Now this is something that's pretty new, and actually is only implemented currently with NVIDIA. But I'll go through what it is. So, first of all, let's look at migration in general. So let's take a simplistic view of VM migration in Xen. We'll not worry about GPUs at this point. This is just a straightforward VM. So we have a VM on the left here. It's got some vCPUs, it's got some memory, and we want to migrate it from that host on the left to the host on the right. So the first thing we have to do is create a new domain in the other host, which is just empty. It's a shell, and it's just waiting there to receive information from the source host. So the next thing we do is we copy across the memory image of that running VM on the source host. But because the memory image can be quite big, it can be multiple gigabytes, this can take some time. So we don't want to do it with the source domain paused. We want to leave that domain running, and we want to copy the memory across. But obviously that means the memory image we're copying is not consistent because it's being updated as we're copying it. So what we also need to do is we need to turn on what's called dirty RAM tracking inside the source hypervisor. So when the guest writes to a page, Xen traps the access as a page fault, sets a bit in the bitmap, and then allows the access to proceed. So that way, every time we iterate around copying the memory, we know what's been updated since we last copied it. All dirty pages need to be copied again after each iteration. And hopefully, if we're doing our copy frequently enough, we will gradually converge and that dirty set will shrink and shrink. But eventually, even if it doesn't shrink to a particularly small size, Xen will call time and it will have to copy the remaining memory image across. So we pause the source domain at this point. That means that memory is no longer being updated. We then copy the remaining dirty pages we find in our map. Now we've got a consistent memory image on the far side. Now we copy the architectural state of the VM, so that's the vCPU state, timers, interrupt, maps, etc. across the target domain. And now we can unpause the target domain. It is a complete image of the original VM, and now it can start to run. And then there's one remaining thing to do, which is we have to free the source domain to release the resources back to the source hypervisor. So that's migration in a nutshell. So let's have a little more complexity. Let's consider a VM that has an emulator. So we're just talking about a straightforward software device model at this point. Now, that emulator, at some point, may wish to emulate DMA. In other words, it's going to map the guest's memory and it's going to do some writes to it. Now, this is fine because the emulator, being in software, all it needs to do is to tell Xen that it's done that. So it updates the dirty map directly via an API. So that way, in the same way as we did before, when we do our rounds of iteration, we just use the dirty map to decide which pages we need to copy again. And as long as the emulator is being truthful, we will end up with a consistent memory image. So now the source domain is paused, the source emulator is paused. We copy the architectural state as we did before, but the emulator also has typically some internal state, so we ask it to export its state, and we copy that into a new version of, or a new instance of the emulator running on the target hypervisor. And then we can unpause the target domain and target emulator and service emulation requests. Now let's add more complexity by throwing in a GPU. Now, the GPU is a piece of hardware, it's not a software device model. So, unfortunately, unlike software device model, when the GPU does DMA to the guest memory, it's not tracked. Current hardware is unable to do this. There is no faulting in an IMU, so we can't track memory. So the only thing we can do is to consider any page that is mapped to the GPU to be persistently dirty. Now that means that all GPU pages are dirty in that map on the final stop and copy. So that stop and copy phase can now be quite lengthy, depending on how much memory is mapped through the GPU, which is dependent on the workload running inside the VM, i.e. the number of applications you've got open and whatever they're doing. So also, one more thing we have to do, apart from that lengthy stop and copy, is the GPU itself may also have some internal state which we need to replicate on the GPU on the far end during a migrate. So there's an extra step we have to do. The GPU device model running in the emulator may have to get the GPU to DMA some of its state through so it can be copied across and DMA'd down to the GPU on the far end. So this is an example of NVIDIA Grid, which I'm going to rush through because we're getting short on time. So this is a new feature of XenServer 7.4. And on the source side, NVIDIA had some library functions to be used by the discrete emulator. These broadly say start live memory tracking, extract the data to be transferred, quiesce the GPU, i.e. the final phase of copy, and extract the remaining GPU architectural state. On the target side, there's new functions to start up the virtual GPU quiesced, i.e. like a shell waiting for some data, receive data from the source GPU, and then unquiesce the virtual GPU context and allow it to start servicing the applications. Another example is Intel GVT-g. Now we have to copy the global GTT state across when we do a migrate. And one of the complexities in that is that the slot we want to copy the global GTT state into may already be occupied. So we have to reshadow into a different slot, and that actually makes life a bit more difficult, as I'll come to in a moment. Now remember, the PPGTTs, they're in guest memory, so they get copied as part of the guest memory image. So all we've got to do is, after the migrate, we rewalk the root pointers and reshadow all of the PPGTTs. But that base pointer makes things slightly different, because that means that the actual virtual address base that the GPU is using has been moved, which means we also have to look at the things that the PPGTs are referencing, the GPU commands, and they may contain embedded addresses, so we have to do some translation on those as well. Now we also have to migrate the render engine, so anything that's been queued on the source hypervisor for the guest we're migrating, those commands have to be extracted from the command queue and transferred into the command queue on the far end, and they may also have to have translations done on them as they go. But once that's done, we can unpause the guest on the far end, and essentially it now proceeds to service the applications inside the migrated VM before migration is now complete. So in conclusion, I'd just like to go through the main points. We've looked at all three vendor variants of virtual GPU in XenServer. As of 7.4, they are now all available in XenServer. NVIDIA Grid virtual GPU migration is also now available in XenServer. Intel GVT-g is not available yet in XenServer, but it is available in prototype form on Intel's Xen kernel and QEMU branches, which can be accessed at that URL. And now, if there's any time, I'll take a couple of Q&As.
Yes, thank you very much, Paul. It was a really great presentation. I like your examples, and I really appreciate that you demonstrated new technologies for us. And we have a few more minutes to ask some questions. Please. Who wants to ask some question, please raise your hand and you'll get the mic. One person? Yeah.
Thank you very much. I would like to ask a question. Is it possible to migrate GPU computations processes for GPUs with different computing capabilities? Is this supported or partly supported?
Currently, with NVIDIA, I believe the latest Pascal hardware will allow you to migrate GPU across. Migration at the moment is strictly between identical chips, though. Now, this is something that NVIDIA have thought about. In other words, what they do on the source and target domains is they allow the Xen tool tag to extract some abstract compatibility information. And then we compare the compatibility information to determine whether we can migrate. Now, at the moment, that means the GPU is identical, but in future, they may allow us to take compatibility information and then determine whether we can migrate from, say, an older GPU to a newer GPU that then runs in some form of compatibility mode.
One more question. If you have complicated structures with pointers in GPU memory, while you migrate to another GPU, are these pointers preserved or there may be some conflicts?
Well, in the NVIDIA case, because the pointers inside the commands are pointing into the VRAM inside the GPU, we don't know exactly what NVIDIA are doing, but we're assuming that when they replay the state of the target GPU, they can put things in broadly the same places, or they have some mechanism of translating those pointers at that time.
Okay, thank you very much.
And we are really tight on schedule. One more hand there. So the last question for now. And everything else you can ask Paul somewhere at the coffee point.
So there is a question. If we have few physical GPUs on the physical layer, can DOM0 provide it to DOM-U it as one virtual GPU?
Sorry, I couldn't quite hear.
Okay. We have a case. We have few physical GPUs on the physical layer, and can DOM0 provide it to DOM-U it as one virtual GPU?
At the moment, virtual GPU is strictly one instance per VM. Now, there's no reason why we have to maintain our restriction on one virtual GPU per VM. But when you're doing graphics workload, there's little point in providing multiple slices of a GPU. You may as well just provide a single bigger slice of a GPU when you're passing it through to a VM. But obviously, if you want to do something like provide, say, 2 full GPUs through to a VM, then you can do that. Now, you can do that using pass-through at the moment. I think the tooling inside XenServer won't quite work correctly, but theoretically you could do it. But when it comes to virtual GPU, I can understand there may be a use case where you want to provide a slice of an Intel GPU and a slice of an Nvidia GPU in the same system through to the same VM. Again, the tooling doesn't provide that at the moment, but it's not something that would be particularly hard to add.
All right, thank you very much. One more time.